Hi everyone, in this video I'm going over the solutions to the homework that I recently assigned my regular non-AP, non-honors physics class. So these are problems having to do with drawing electric fields, as well as calculating forces on charged particles due to electric fields, and then finally using Coulomb's law to calculate the force on a particular charged particle due to one or more other charges. So in the first problem, it was actually the first three problems, it was about drawing electric fields due to charges or charge distributions, and we have a positive charge in 1A and 1B a negative charge. In 2A we have two equal magnitude oppositely charged particles, and in 2B we have two positively charged particles where one of them has 3 times the amount of charge as the other. In 3A we have a negative bar of charge, and in 3B that has been wound into a U. So your answers should end up being something like this. Notice that from the positive charges, the field lines point outward. They point inward toward negative charges, and the number of field lines coming from or going into a charge is proportional to the size of the charge. So notice that in 2A we have a symmetric situation because the magnitudes of the charges were the same, but in 2B we do not, because we have the charge on the right being 3 times the magnitude of the charge on the left. So we have 3 times as many field lines coming out from it. Also notice that starting later on in 2A, I stopped being neat with my charge lines, or my field lines, and just tried to get the problem finished because it was taking too long. Though in 3B, there was something to be shown here. So I did make this at least somewhat neater. Notice that the electric field is extremely strong going into the middle of this horseshoe shape here. That's something to keep in mind with this type of charge distribution. And otherwise, stuff like here in 3A, this is not exact, this is not perfect, and you can probably get a better idea by using an app. Now, another problem that was assigned, a proton feels a force of 9.5 times 10 to the minus 21 newtons. So what's the strength of the electric field in which it's immersed? So we have our givens, and the force due to an electric field on a particular charge is F equals QE. So, because remember that's just the definition of the electric field, force per unit charge, so plug in the numbers and you get 0.0593 newtons per Coulomb. That is not a very strong electric field, but it's still something that's kind of measurable in a manner of speaking. It's just that a proton has an extremely small amount of charge, so it also feels an extremely small amount of force. How about another proton being immersed in a known electric field of 32 times 10 to the 8 newtons per Coulomb? That would be 3.2 billion newtons per Coulomb. That's a fairly strong electric field. And there are plates separated by 0.082 millimeters. So what is the voltage connected to the plates? So we use a famous equation relating voltage of charged plates with the electric field that's between them, separated by a certain distance, and that's V equals Z. V equals ED. So plugging in the numbers, you get 2.6 times 10 to the 5th volts, or 260,000 volts. Now in problem number 21, an electron is immersed in an electric field of 20 newtons per Coulomb. What force will it feel? So, relatively weak electric field as electric fields go to some extent. Notice the charge on the electron is negative, but here looking at the force, so first we'll just calculate the magnitude of it, so I slapped absolute values bars around everything. Plugging in the numbers, we get a force of 3.2 times 10 to the minus 18 newtons. Now, again, since it's an electron, and electrons go in the opposite direction, or at least they feel a force in the opposite direction of an electric field because they're negatively charged. That means that the direction of the force is opposite to the direction of the electric field itself in this problem. How about problem 72? We have two electrons separated by 1 micrometer. Question is, what is the net force, in this case really just the force, on the electron on the right due to the electron on the left? So here's our setup. We want to find the force on this particular electron. The only particle that's causing a force is the other electron. So we set up Coulomb's law after we write down our givens. We also note that electrons repel, which means the direction of this force is going to be toward the right, in the positive direction as we put it. So we're just going to put a positive sign in front of this. And now we plug in our numbers. getting the magnitude of the force, and that turns out to be 2.31 times 10 to the minus 16 newtons. The direction of the force is toward the right. How about a problem where we have multiple charges, not just two, but multiple charges acting on another charge? So in this case, what is the net force on this minus 2 millicoulomb charge in this setup right here? So notice these separation distances. These are relatively small. So writing out our givens, we have our charges, and we also have our distances between the charges. The distances that we care about, so I've labeled these charges Q1, Q2, and Q3, so 1, 2, 3 going from left to right. So the only distances that we care about are the distance from charge 1 to charge 3, and the distance from charge 2 to charge 3, because remember when we use this superposition principle, we don't care about what's going on between charge 1 and charge 2. We only care about what's going on between charge 3 and each of the other charges. So we're going to calculate those forces separately and then add them up. Notice micro is 10 to the minus 6th, so we needed to convert everything to SI units. Milli is 10 to the minus 3, so that got converted as well. So here's what we're dealing with. The force on charge 3 is due to the force on charge 3 due to charge 1, plus the force on charge 3 due to charge 2. That is the superposition principle. I bolded these because these are force vectors. They could be acting to the left, they could be acting to the right. So first of all, looking at this situation, we notice that charge 1 and charge 3 repel each other because they're like charges, so that's going to mean that there's going to be a force on charge 3 due to charge 1 that goes toward the right. But the force, charges 2 and 3 attract each other, which means that the force on charge 3 due to charge 2 is going to be going toward the left. So that's going to give us a negative result. So setting up our free body diagram, we have this. There's force on 3 due to 1. There's the force on 3 due to 2. So now that we realize this, we can say that the magnitude of the net force is going to be positive F3 due to 1, magnitude minus the magnitude of force 3 due to charge 2. Force on 3 due to charge 2. So here's where we stand. It's time to start plugging in Coulomb's law. Each of these forces has a Coulomb's law associated with it. Remember, Coulomb's law says that the magnitude of a force between two charged particles is proportional to the product of the charges, inversely proportional to the square of the separation distance between the charges, and the proportionality constant is this K, the Coulomb constant. So this is the result of setting that up with our two separate forces. And notice that I have a KQ3 in each of these two expressions, so I'm going to factor that out to make my life a little bit easier when I plug in numbers. And upon plugging in the numbers, we get this result. We get a force of negative 1.34 times 10 to the 17 newtons, which means a force of 1.34 times 10 to the 17 newtons toward the left. So that's the end of the solutions to these problems. So if you have any questions, please let me know in the comments section. And thank you for watching.